question, what is the total mechanical energy of the system? Okay, what comes to mind when you say total energy? What comes to mind? Kinetic plus potential, but we said that the total energy can be it can also be, it's kinetic plus potential at any point, right? But I can also, if I happen to know the maximum velocity, or if I happen to know the max oscillation, if I happen to know the max potential energy, that would be 1/2 kx squared, right, x max? Or I might happen to know that's also equal to E, this is max, right? Or it could be K max, and here I would say 1/2 mv squared max. So do I know any of these? Looks like I know that one, don't I? This is the maximum oscillation. Do I know K? I know that omega is equal to square root of m over K, right? Don't I? Is that the right? I always is that the right formula, or is it K over m? I always get it mixed up. It is K over m. Okay, it just makes it -1. I didn't finish writing. I always forget things. Well, that's why you're looking. Okay. So, let's see. Do I know anything? I know the frequency. I know F, and this is 2 pi F, right? I know the mass, so I can solve for K there. That's probably what they do. Let's see what they do. Let's see how they do it. They might not do it that way.
We square omega.
Yeah. Is that what they do?
Yep.
Okay. So they get K there. They get K, so they have F. So they did follow what we thought there, and then they recognized, like we did, that the maximum displacement, that the kinetic energy will equal the total energy, so that they go all the way out to the end. They say, well, the kinetic energy is 0 out there, and we know this K. We figured it out here, and we get that x squared. Look at that. Get that number. Okay. What's the block's speed when it passes through the equilibrium point? What occurs to you? How do we get the speed at the equilibrium point?
The mv, half mv squared.
Yeah, and at the equilibrium point, the speed is
0.
no maximum. See, maximum, right? So that's equal to the energy is equal to the total energy, then, right? The kinetic energy. So 1/2 m. Here's the mass. V squared. Here's the total energy. They get 12.6. See? What do you think about all that? Think we could do some problems on this order? Thinking about, see, what you're doing here is you're kind of thinking about the motion, where's the maximum potential, where's the maximum kinetic, you know, it's in the middle, all that sort of stuff. Yes, sir.
Could you explain K and 1v?
Here, this one,
Yes.
what is it? Or what are you asking? I'm not sure.
What is K?
K comes from F equal minus Kx. So we're looking at simple harmonic motion, right?
Right.
And we said the key to simple harmonic motion is it follows a Hooke's law restoring force. So you know what the spring constant is, don't you? Right? Or do you? The spring constant is how much force does it take to stretch the spring? So here, there's no weight, and I don't know what that is. We'll say 5 grams or 10 grams or whatever it is. That's so 10 grams a tank that stretches it that far. See? So the force is 10 grams times 9.8 meters per second squared, right? And it stretches at, I don't know, 10 centimeters. That's the force constant. We call that the spring constant. See, we start to drift away from the original definition of K. So when you get a little confused, you say, okay, what is K? You go back, oh yeah, that's the spring constant. What is the spring constant? If someone came up to you at the bus stop, you know, you're waiting on the bus and stuff, you know, hey, you know what the spring constant is? I was reading the other day, and they might ask you. What would you say? Oh, that's just telling you how much force it takes to stretch the spring, right? K is in newtons per yes, sir. Newtons per meter, right? F over X. You know, in physics, you know, the idea of the ratio, this ratio, you see, so important. So important, the idea of a ratio. You know, you see so many ratios. The ratio will tell you, usually 90, I think, it'll tell you mostly what something means. It can be a little tricky. Like acceleration's a little tricky, right? Because sometimes we write it, well, anyway, the idea of the ratio there. So you're back to square one. That happens though, that's a good point you bring up. Where you're in the middle of something and you've got all these, you know, you'll be doing this sort of stuff, working in engineering companies, depends on what you're doing, but you might be, but you might do some development work, or you know, you have to go back to some basics, or use some equations, right? And you look at that equation, you're like, what the heck is that? What is that? You know, you have to figure out, okay, wait a minute now. Because you're responsible to get the numbers right. You need to understand, okay, what is that? Go back and look, oh yeah, I remember that. Might be some exotic ratio or coefficient or something, you know, or some. You have to understand, okay, what is this? Because why? Because you have to, it's all about the assumptions, right? When you're doing something, what are the assumptions behind this set of relationships? And if you violate the assumptions, and you know, if you go out of the bounds of the assumptions, and you're outside the limits of what was derived, huh? Well, anyway, there you go. I hope that helped a little bit. All right, let's. So we went through those, and now here's an angular simple harmonic oscillation, and an angular oscillation is, so instead of a spring you have a wire, and if you twist the wire, it'll oscillate in a rotary motion, you see? So this wire, you can twist it, but it won't deform it. It'll cause it to come back to its original shape. And so it creates an oscillatory motion, right? That's called a torsion pendulum. Here it is here, torsion pendulum. And it oscillates back and forth like that. Now, we didn't do any. Usually in the lab during the regular semester we do different types of pendulums. There's all sorts of pendulums, but we didn't do it. We didn't do it this summer, but you have the torque equal to K times theta. That's the force, right? So, but anyway, it's just showing you that. And here, instead of mass, you have the moment of inertia. So, anyway, I don't usually get into this, so. But it's just a different type of pendulum, but you still have the same mathematics. Because this is a restoring force right? When I twist it to the right, the torque that wants to make it rotate, when I twist it counterclockwise, the torque wants to pull it back clockwise. It's a restoring torque, okay, for rotation. But anyway, we just kind of went through that.
So that's the same thing in the harmonic balance on the cars?
Um,
Yeah.
a harmonic balancer,
That's gonna be more.
I'm trying to remember.
That's gonna be
Harmonic balancer. Oh,
So we're like in the firewalls of the car, you know, when like the transmission starts.
where's the harmonic balancer? Choose
I
the,
think we have them on automatic cars. And then like manual cars has a line.
you know, honestly, I don't remember. I've changed harmonic balances, but I don't remember. I remember being in the front. Where are you saying there?
When we're like in the middle of the, between the, no,
I don't remember exactly. I think the function of a harmonic balancer is to minimize resonance oscillation, or resonance oscillation. I think that's what they do, but I forgot. I have to look it up. You must do work on your car or something. Yeah. I don't remember. They may have them all over the place now, for all I know. It's a mechanical system. Okay. Well, let's see, pendulums. Here's a pendulum. Let's look at this. So we're more or less skipping this angular oscillator. We're just sort of covering it. We won't cover it on the test, okay? We will not cover that on the test, but okay, here's a pendulum, circular motion. We'll take a break here in just a little bit. Here's a simple pendulum. So, in a pendulum, then you have the mass on the end of the string. Hold it down, guys. Hold down a little bit. Thank you. And you have a restoring torque. And so, the torque is the length multiplied by the force, and the force of gravity. When you swing the pendulum out here, right? Here's the force of gravity, and this is the component of gravity that pulls it back. So when you displace it this way, there's a restoring force that way. And that is F sine theta. But this is also an arc length here. Arc length is equal to L times the angle theta. And so the torque is L times the force, right? There's a force acting at a radial distance from a point of rotation. This is the point of rotation. And that turns out to be L FG sine theta. And they go through a little derivation here where the torque is equal to I times alpha, and this is the moment of inertia, and this is F sub G is just M times G, and where are we going with this? They solve for alpha, they get MGL over I times theta, and then they recognize that that MGL, that this term here is just like, it's the angular equivalent of simple harmonic motion, right? If I multiply by M, so I have F equal minus K times theta, or torque equal minus K times theta. This is a constant. This is like the spring constant, and that's the angle of rotation, so they're saying it's just like simple harmonic motion, and if we use the equations we have there, we wind up with the expressions omega is mg over L, and period is 2 pi I over mg L. Now for a pendulum, I is equal to m times L squared. They substitute, cancel. Here's what they wind up with. For a simple pendulum, the period is equal to, where is it? Square root, period equals square root of L over G. So, we just have that simple relationship. Then they talk about the physical pendulum. And physical pendulum, normally, you have all the mass concentrated at a point, but in a physical pendulum, you have the mass distributed in any shape that you want, right? So this can, if I put a hole through here, this can act like a pendulum, right? But it has, not all the mass is not located at the bottom. So, calculate the moment of inertia, they have a simple equation for that. So I don't usually go through all this stuff on the test, but I mentioned it in class. You have the period equal 2 pi I over mgh. Right. The reason I don't go through it is it's just so basic, so simple. It's just, but anyway. Okay, let's go on. Skip this stuff.
Sir,
Yes,
excuse me, I didn't get the point about the torque.
the what?
Torque.
Say it again.
T-O-K. Torque.
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 Oh, torque.
Yeah.
What did you get? We didn't cover torque. We didn't cover torque.
He's talking about the restoring torque.
For the simple pendulum?
Yes.
Well, what are you confused about? What torque is?
Yes.
It's a force. We didn't cover torque. Remember we said, do you want to cover rotation or do you want to cover oscillations? So we didn't cover torque and rotations. We only have so much time in the summer. But we can go over torque. What torque is, okay, we'll go over torque. You want to go over it? We can go over the general definition of it. So, what torque is, if you have an object, here's an object, here, have this bag, you see, or maybe this, I don't know, got it on here. Use this one. Here's an object. So, it has this, that might be all right, but this might be simpler. It has a center of mass, right? So, if I push on it with a force, right? If I push through the center of mass, right, if my line of force goes through the center of mass, then the object will go in a straight line. Okay? Or if I push it this way,